Modern upstream operations manage volatile physical forces at a staggering scale. Fluid is extracted, separated, and pushed through vast steel infrastructure under immense pressure. Governing this physical network requires solving a persistent equation. Upstream performance is strictly a demand-supply balancing problem. The supply variables are highly dynamic. Operators must manage thousands of individual, heterogeneous wells, each governed by its own unique decline curve, competing for shared surface facilities and finite intervention crews. The demand variables are equally rigid. The network must satisfy strict facility throughput limits, ensure constant export readiness, and meet inflexible national production commitments. The industry standard for managing this equation contains a severe structural flaw. Execution decisions are calculated locally, constrained to the perspective of an individual well or a single pad. When every well attempts to maximize output simultaneously, volumes clash at shared infrastructure. Hidden constraints surface reactively downstream, overwhelming capacities. To protect facilities, operators rely on wide-scale throttling, resulting in unnecessary deferment and severe value leakage. This chronic inefficiency persists because upstream operations lack a single execution system that owns the end-to-end demand-supply balance. Correcting this requires abandoning reactive coordination and moving to active, system-wide orchestration. Maximizing the flow rate of an individual well serves no purpose if that localized push destroys the stability and economic value of the entire downstream network. The Opti Upstream Suite, or OUS, resolves this through a bifurcated two-layer autonomous control architecture designed to balance the entire value chain continuously. The base unit of the lower execution tier is the Autonomous Optimization Model, or AOM. It ingests incoming demand and live supply capabilities to generate specific operational commands. Its scope is strictly bounded to a designated physical asset. Operating continuously, an AOM adapts to shifting field conditions, calculating and issuing operational decisions every few minutes. A dedicated well performance AOM, for example, measures live well potential and decline behavior against downstream readiness signals like gas compression availability and storage capacity. These models rely on an engineering principle known as constraint-native design. Physical and operational limits, maximum gas-to-oil ratios, water handling thresholds, and precise processing capacities are hard-coded directly into the decision logic of the model. Legacy software treats limits as post-execution checks or relies on operators to manually apply overrides after an unfeasible plan is generated. By embedding constraints natively, local execution decisions are mathematically blocked from issuing any operational command that violates the physical limits of the field. This logic scales rapidly when individual wells feed into a shared pad infrastructure. The pad coordination AOM takes ownership of balancing shared capacities. If a specific manifold reaches its physical limit, the AOM reorganizes the load. It autonomously redistributes flow rates across connected wells, prioritizing production without requiring manual set points. Moving further downstream, the surface constraints grow highly complex, requiring the facility throughput AOM. This model analyzes inlet production rates and equipment utilization to pinpoint the true binding bottlenecks at the processing surface. Once a bottleneck is identified, the facility AOM determines the exact upstream locations where production should be constrained to absorb the limits safely and economically. Distributing AOMs across the network stabilizes local domains, but it introduces a secondary hazard. Specialized control models optimizing their own zones can inadvertently cannibalize the stability of adjacent operational domains. A network of perfectly optimized local operations will still fail if those local models execute actions that conflict with the enterprise's broader economic commitments. To resolve this, the architecture deploys its top tier, the orchestration layer, driven by OPI. OPI has a strict operational boundary. It does not execute direct field-level actions. Instead, OPI governs the system-wide demand-supply balance, setting overarching economic priorities and resolving cross-domain trade-offs. It operates on an entirely distinct cadence from the execution layer, evaluating constraints and testing scenarios on daily, weekly, and monthly cycles. For example, OPI runs integrated production cost analytics to analyze the economic health of the portfolio. It dictates which high-lift cost wells the execution layer should optimize and which it must shut in to protect portfolio margins. OPI also analyzes system-wide recovery urgency to dictate exactly where scarce mobile resources, like rigs, crews, and intervention capacity, must be allocated to maximize enterprise value. The synergy between the two tiers is absolute. OPI defines the mathematical priorities and the economic boundaries. The execution AOMs act autonomously, but entirely within those approved guardrails. Separating orchestration from execution guarantees that a real-time adjustment made at a remote wellhead is always tethered to the overarching economic reality of the enterprise. The true capability of this architecture is exposed not in steady state, but during a sudden disruption where the demand-supply balance is instantly shattered. Consider a mechanical trip that causes a sudden, severe drop in water handling capacity at a primary downstream facility. The traditional response involves alarms triggering across local control rooms, leading operators to execute rapid, conservative curtailments across the field to prevent a system-wide failure. Under OUS, the exception orchestration AOM instantly detects the sudden supply-demand mismatch at the facility. The signal is pushed up to the OPI layer, which instantly recalculates system priorities to account for the newly constricted water limit. OPI immediately issues updated, highly restrictive guardrails down to the execution AOMs positioned across the field. Bound by the new constraints, the execution AOMs autonomously throttle production, but they target only the specific wells currently generating high water cuts. The sudden constraint is absorbed safely by the network. Because the response is surgically precise, the high-performing, low-water oil wells remain untouched, maintaining maximum possible yield. The upstream network successfully rebalances itself without a single manual intervention, replacing reactive firefighting with governed recovery. This moves past standard task automation. The system actively automates the execution of complex decision-making under severe physical constraints. By unifying governed orchestration with autonomous field execution, upstream operations evolve from a fragmented collection of manual tools into a resilient, economically disciplined operating system.